Okay, kids, it is Friday evening, 20:07, and I'm just not getting around to getting this lecture recorded because my room has been trashed. I kind of get it all back together, and I'm missing a bunch of stuff, including the adapter that goes from my iPad to the projection system, so this is why I've got this drawn up here. So I'm going to have to wing this and give you some visuals at the same time. This is not how I wanted it to work, but we're going to make it work, so bear with me. Okay, so let's talk orbitals. So if you look at your basic carbon atom, okay, which has 6 electrons, 1 s2, 2 s2, 2 p2. Okay? So let's look at you to understand hybridized orbitals, you have to understand how a normal carbon structure is going to be. So what I've got drawn here is like, imagine that you have an X, Y, and then you have like a Z axis. So atoms exist in 3 dimensions, even though we typically just draw them in one plane, because that's how we do it. So imagine that you have an X, a Y, and then this Z is sticking out. So when you look at the shapes, S's are spherical. Now, the one thing I've got to begin to get out of your minds now, because everybody thinks these electrons travel in these nice little circles. We really don't know what the electrons are doing. We can talk about them in terms of probability, okay? So Erwin Schrödinger was the first one to come up with like a mathematical treatment of a probability function for a wave. And he came up with his equation, the wave function, which was the Greek letter psi. And psi represents the wave probability functions. If you ever get a chance to do this, it is some of the most difficult math you will ever do. Like one problem literally takes you like 1 page to do. It sucks. It's horrible. But it's really cool when you get done. Obviously, I'm not going to make you do that. But here's what it does, is that it describes the motion of an electron as a wave of probability, which sounds odd, but that's actually what it is. It's a wave of probability. So when you look at these spherical shells, we're not saying that they move in circles. All we're saying is that this is the highest region of probability, is a certain distance away from the nucleus. So this 1s, it's capable of holding these 2 electrons, and those are closest to the nucleus, and those are going to be the most tightly bound because of you have negatively charged particles very close to the positively charged nucleus. So one of the things they struggled with was how come those electrons just don't spin in and collapse into the nucleus? Well, because it's a wave function, it can only get so close and still complete a wave. So that's why those electrons and everything don't collapse in. And it's a good thing they don't. Because if all of these electrons collapsed into the nucleus, we wouldn't be here having this discussion because you could not have stable atoms. So it's a good thing these electrons don't end up collapsing into the nucleus. Okay, so here's what's going to be important. So we have 1s here. Here's this first shell. It can only hold 2 electrons. This is why the first row of the periodic table only has hydrogen and helium, because that's the only, you can only put 2 electrons in that first energy level. Now, then you go out here to 2s, okay? So we got 2s2, so there's going to be 2 more electrons out here in a higher probability, just another region of probability. Now, the p sublevels. P stands for pair shapes. Now, here's the most common thing everybody says, oh, these electrons travel like in figure 8 patterns. No, that's not what we're saying. It's not what we're saying. This is not, when you see circles like this, that is not the path the electrons take. These are just regions where you are most likely to find your electron. It's kind of like Bruce, okay? On Monday morning at 11:30, when we're going to have our next Google meeting, there's a very high probability that Bruce is going to be sitting in his comfy gaming chair with a headband, okay? Now, I can't guarantee that, but that's a very high probability. There is a chance Bruce might be in Paris. There's a chance, okay? I'm not saying it's a very high probability, but there's a chance Bruce could be in Paris. Bruce could be on the moon. Again, likely to happen? No, but there is a possibility. So when we're talking about where these electrons are most likely to be, it's a region of probability that says, hey, around the nucleus in the p sublevel, and both of these exist to complete one orbital. Because remember, in the p sublevel, there are 3 orbitals. Each orbital can hold 2 electrons. There's a total of 6. So this is why when you look at the periodic table, right, you've got your 2 columns here, lithium and barium. And then over here, then you have 6 columns over here, which is filling up that potential p sublevel that can hold 6. And then you've got your d sublevel here, that holds 5. Orbitals can hold 10 electrons, and then down here your lanthanide and maculating series, those are your f sublevels, those can hold 7 orbitals, for a total of 14. So, and here's the beauty of what Mendeleev did in terms of laying out the periodic table. They had no concept of orbitals or anything like that. But he just saw the pattern, and then later on we were able to figure out, oh, this is why it works, is because of the distribution of the electrons. Now, here's what's important. In a non-hybridized carbon atom, listen to me, in a non-hybridized carbon atom, what you have is that you would have 2 electrons in this inner sublevel. You're going to have 2 electrons in this orbiting somewhere around here. And then you're going to have a couple of electrons somewhere in one of those p orbitals. Maybe one in the x, maybe one in the y, maybe one in the z, I don't know. But here's what's going to be important, is that when you're going to form bonds, listen to me, listen to me, listen to me. When you're going to form bonds, you need a single unbound electron. So here's the problem. With a non-hybridized carbon atom, you only have these 2 electrons in the p sublevel that are capable of forming bonds. Okay, that's going to be important. In non-hybridized, I've got only 2 electrons that are available. Creates a problem. Now, once they figured out the ability to actually look at the structure of molecules, which was tough, okay, most of the time it's done with X-rays, ironically. Because it isn't like, you know, so here, for example, I've got a methane molecule, okay? And it looks very static, right? Oh, here's a central carbon atom, and I've got 4, you know, hydrogen atoms around it, and everything looks stable, and it's cool, and woo, okay? Yeah, this is so far away from reality. You've got, you know, here's your central carbon atom, and it's got these 6 electrons that are buzzing around, and then you've got this hydrogen nucleus, and you've got 1 electron buzzing around out there, and it isn't like we can like take a picture of it. So here's the problem with this. It models it very well, but it's a horrible model in terms of reality. Because these actually just represent the nuclei, and the carbon nucleus is bigger than the hydrogen, and so in that regard it matches that. But here's what's important, is that this isn't reality. This is a nucleus, you've got 6 electrons going around. So it's tough to actually figure out what that structure is, because it isn't like we can look at it and take a protractor and measure the angle and go, oh, it's 109.5 degrees, okay? Like I could sit here, oh, I can take a protractor, I can measure that. Oh, it's 109.5 degrees because everything is static. It's not what happens, okay? Not in any way, shape, or form what happens. But here's what is important. When you look at a methane molecule, the bond angles are 109.5 degrees. If there's ever a number that you memorize for those of you who are taking the AP exam, in case they happen to throw this random question out there of a bond angle, 109.5. When in doubt, answer 109.5. It's like if you're asked a baseball trivia question, when in doubt, answer the New York Yankees. It might not be right, and I hate the New York Yankees, but at least odds are, hey, it might be right. Okay, so here's the disparity. If it's a non-hybridized carbon atom, everything is going to be at a 90-degree angle. 90-degree angles don't match the reality of the structure of this. The other problem is that I don't have enough single electrons to make this happen. So here's what happens. And this is this sp3 hybridization. So what happens is that we take the 2 electrons that make up the inner s orbital on the second energy level. We also then mess with all of the p orbitals, and this is going to be important. So on sp3 hybridization, implied that there's a 1 out here. So what happens is that the sum total of this is actually 4. So what happens on sp3 hybridization is that we screw up the s and we screw up all 3 p orbitals. So this is going to be important later on down the road. So if you have sp3 hybridization, it adds up to 4. And here's what's important about that 4. It tells you how many orbitals got jacked up, and it tells you how many regions of what we call high electron density there are around the central carbon atom, okay, or nitrogen or oxygen or whatever it is. Now, here's what's important. Es muy importante. In carbon, in methane, each one of these is holding and forming a bond with a hydrogen atom. What's important when we get into methane and water is that you can also have unbound pairs of electrons in these hybridized orbitals. Okay? So this is sp3 hybridization. This is like the quintessential idea of sp3 hybridization, because, and it's the simplest one to look at. So I've taken the 3 p orbitals, okay? Those are all jacked up, and the s. So let me erase this, and I'm going to draw the sp3 hybridization. So what's going to happen, by the way, it's like 80 degrees in this room, and I'm really, really hot. So here's what's going to happen. You've got the central carbon atom, there's your nucleus, and then this will make sense in just a second. Okay? So there's the carbon nucleus. So what's happened is that, so this is what we're looking at. So here's the central carbon atom. I've got one of these in the plane of the board. I've got another one in the plane of the board. I've got one coming out, okay? And this is what this is showing. This is like this heavy dashed line coming out like this. And the dotted line is the one that's going back into the plane of the board. So I've got 2 that are in the plane of the board, one that's coming out, this is like this dark wedge, and then I've got a dashed line going back here. So right now, each one of these is holding 1 electron, because I'm loading methane. So I've got 4 electrons. So here's a hydrogen, it overlaps with an electron. Here's a hydrogen, it overlaps. Here's a hydrogen, it overlaps. Here's a hydrogen, it overlaps. Okay? So what I've got here, I've got this one central carbon atom. This is this sp3 hybridization. Now, this bond angle, this is what on the sheet that I gave you, this is going to be important. This is 109.5 degrees. Now, that's a pretty high degree of precision if you think about, it isn't like, it's about 100. We got this down to like 109.5 degrees. We got this angle down to like the nearest 10th, okay? For something that is so incredibly small. And this is one of the great triumphs of chemistry and physics, was actually to be able to measure these angles in something that isn't solid, okay? It isn't like, we draw it like this, but it isn't like there's a stick on an atomic level between a carbon and a hydrogen, and we take the world's smallest protractor and we hold it up and we measure it. That isn't how it works at all, okay? Okay, so sp3 hybridization. With methane, each one holds a single unbound electron. I've got 4 regions of high electron density. All 3, and this is going to be important, all 3 p orbitals are hybridized, and the s is hybridized. The inner s, that first s, isn't touched. So this is important. I cannot emphasize this enough. When you have sp3 hybridization, you screw up that second S sublevel, and you screw up all three P sublevels, okay? All three P sublevels are hybridized. Because later on when we get into sp2 and sp hybridization, you'll see that it's important that we leave some p orbitals not jacked up. Okay, so you got this idea. We're good, we're solid. Okay, so, I don't even know what that's going to say. So, let me move this over here for just a second. Okay. So I'm going to run through all of these and I'll go back over to the board. So let me kind of shut up for a second. It's tough doing the camera work and everything at the same time. So these are the lecture notes that I sent you. So here's methane, bond angle 109.5 degrees. That's going to be important later on. Here's sp3 hybridization. I've screwed up the S, all three. This is an even distribution because Mother Nature is lazy. She goes, okay, hey, if you're going to have these regions of high electron density, I want these to be completely spread apart as far as you can, and this is the most even distribution that we can get. Okay. Now, the next one we're going to talk about is ammonia. Okay? So here is ammonia. Now, here's what's going to be important with ammonia, and I'll go through this in just a second. Ammonia has 5 valence electrons, okay? Carbon had 4. Nitrogen has 5. So what's going to happen is that this is still going to be sp3 hybridization. So what's happened here is that I've still screwed up the S and all 3 p orbitals. But nitrogen has 3 valence electrons, okay? It has 3. So it's going to form a bond here, a bond here, a bond here. That leaves 2 extra ones. And this is going to be this unbound pair of electrons up here. So this is what we call this dome of negativity. If you ever hang around people that are always negative, okay, they're like an unbound pair of electrons. There's just this dome of negativity around them. Don't hang around with people like that, and certainly don't be a person like that. Nobody's going to like you. Okay, if you think everything in the world is wrong, you're going to have a miserable existence, and you're going to make everybody else around you miserable. Okay, small editorial statement there. Okay. So, here's what's going to be important. I've got a dome of negativity. Now, what's going to happen is that this is going to make this a polar molecule. Methane, which has this even distribution, is nonpolar because of the fact that everything is symmetrical. There isn't this region where you have more electrons. This is like completely symmetrical. So, this ammonia has, because it has this dome of negativity, these unbound pairs of electrons, this is important. This is going to make it a polar molecule. Now, one of the things we're going to get into is what's called a dipole moment. A dipole moment is represented by an arrow that points towards an unbound, like a region of high electron density. So, everything here is pretty cool and that's balanced out. So, when we get into dipole moments, this is going to be represented by an arrow that's going to be pointing up. So ammonia is going to have a dipole moment, and it's going to have an arrow that's going to point up like this. So this is why, if you remember the demo that I did with ammonia and I dissolved it in water when we were talking about weak bases, ammonia very much dissolved in water, because here's the deal with dissolving. Likes dissolve likes. Ammonia is a polar molecule, therefore it will dissolve in water. Now, when you generate hydrogen gas, okay, drop a piece of magnesium and hydrochloric acid like we did on the entropy lab. Hydrogen gas bubbles up. Hydrogen gas is a non-polar molecule because it's balanced out. Oxygen is that way. But ammonia is very polar. So ammonia is actually very soluble in water because it's polar and water is polar, therefore it dissolves within them. Okay. Now, here's the other thing. Notice that this bond angle was down to 106.8. The other one was 109.5. This bond angle was getting smaller, and here's the reason why. This dome of negativity up here is created by electrons. These bonds are formed by electrons. So basically what happens, these are like buoys, okay? So these bullies up here are forcing this bond to get closer because you've got this dome of negativity up here that's creating this region of negativity, which is forcing this region here to be scrunched up a little bit because these electrons, because they're negatively charged, don't like these electrons here because they're also negatively charged. So this is going to force this bond angle down a little bit. Okay, now, then you're going to have, for the last one, Malagma, okay? Pula, if you are in Setswana, or Botswana, you're speaking Setswana. Vula, if you're in Setswana and you're speaking, or if you're in Botswana and you're speaking Ikalunga. So, here's the deal. So if you look at a water molecule, okay, we have water. So now, here's what's happening here. Notice that this bond angle is even smaller. It's dropped to 104.5 degrees. So oxygen has 6, count them 6 valence electrons, okay? 6. So what happens is that 2 of the electrons are going to be bound up here, forming bonds with the hydrogen. That leaves 4 more that are going to lurk out here. So ammonia only had 1 dome of negativity. Water actually has like a bigger dome of negativity because now you have 2 unbound pairs of electrons. So this is why this angle has become even smaller, because now you have more electrons out here that are making these smaller. Now, here's what's important. All 3 of these have sp3 hybridization, and you're going, Mr. Burkham, whoa, stop, man, stop, whoa. How can it be sp3 hybridization when you only have 2 hydrogens? I was cool with methane, CH4, cool, sp3, it adds up to 4. There's 4 hydrogen atoms, I'm digging it. How can this be sp3 hybridization? So it's sp3 hybridization because of the fact that we said it can, that hybridized orbital can do one of 2 things. It can either hold a single electron to form a bond with hydrogen, or, wait for it, but wait, there's more. For additional shipping and handling, it can also hold unbound pairs of electrons. So this is still sp3 hybridization. Got an unbound pair of electrons here, an unbound pair of electrons here. So you have this huge dome of negativity, a hydrogen here, you've got a smaller bond angle. Okay? Digging it. Digging it, digging it, digging it. Okay, now I'm going to turn the lights back on and I'm going to go back over there and draw on the board for just a second. Okay, so let's talk ammonia. So nitrogen, 1s2, 2s2, 2p, 3. So you got a total of 5 valence electrons, and here's nitrogen, hydrogen, hydrogen, okay, hydrogen, and then you've got this unbound pair of electrons. So here's the structure, right? You got a nitrogen, a hydrogen in this plane, one sticking out, one coming back here, and then this dome of negativity. So this is still sp3 hybridization because there are 1, 2, 3, 4, a total of 4 regions of high electron density around the central nitrogen atom. Same thing is true of methane. So methane has 4 regions of high electron density, but each one of those is forming a bond. Ammonia also has 4 regions of high electron density. One of those just happens to hold a pair of electrons up here. And again, because of this dome of negativity, it's creating pressure to force these together. But the other side of it is, these electrons here go, whoa, 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 Jack, back off me, big man. Because they don't want to be near each other either, because they don't like each other. So there's a limit to how much negativity this can create in terms of forcing these together. Because they're going, hey, we're going to stand up for ourselves too. We don't want to be near each other. So it's imagine like, you're in the back seat of the car and you're on this long road trip, and you've got your little brother that you really don't like, and mom and dad are saying, hey, you have to sit close together. It's like, no, we don't. It's like, he's touching me. And mom and dad are trying to here's this negativity thing, because mom and dad are really getting tired of you bickering. He touched me, he's looking at me. It's like, gosh, shut up. Okay. All right. So, sorry. It's 5:07 on Friday night, and I haven't had dinner, and I'm hot, and I'm sweaty, and so I'm a little punchy at the moment. So, with that said, so now we're going to talk about water. Now, if it weren't for water, as a species, we wouldn't be sitting here having this discussion. Because the cool thing about water is because it has, just like ammonia, okay? So, ammonia is going to have a dipole moment. Guess what? Oxygen's also going to have a dipole moment. So you represent dipole moments with arrows pointing in the direction of your electron pairs. So water, because it's so polar, this is why it's such a good solvent. This is why so many things dissolve in water. Now, when they first, the logical thing that you could almost argue with water is that why isn't water linear? Okay? Why doesn't it exist like this? Okay, you've got 6 electrons around the oxygen atom. Why isn't it linear? Because if it was linear, I promise you, if water was linear like this and non-polar, we wouldn't be here having this discussion. Because water could not exist as a liquid if it was in this structure. So the good thing about water, and that's what allowed evolution to take place, is because you had, and why we have oceans, and why water has so many unique properties. It's a solvent, it's great. So, because of the fact that it's not linear, is the only reason it's not linear is because it goes through this sp3 hybridization. You go, Burkamp, how can it be sp3 hybridization? There's only 2 hydrogens. Oh, listen to me, Sensei. It's sp3 hybridization because those other 2 orbitals are holding unbound pairs of electrons. This is why you have this structure. Now, if you notice what happens, water angle is down to 104.5. So again, now you've got these 2 regions up here that are trying to force these water molecules together. They're trying to force these hydrogens together. They're trying to, because it's got this huge dome of negativity, but again, there's a limit to how scrunched they can get, because these are also repelling each other because of the fact that they are also electrons. So, it's now 10 after 7. It is 80 degrees in this room. I'm tired, I'm frustrated, I haven't eaten. I can't find my little adapter. And so, I think I've put in enough time trying to get this explained. I'm going to finish this up tomorrow and send this out. Guys, I'm going to go home and I'm going to get on my iPad and draw with that and eat supper. So anyway, have a good weekend, kids, and I will finish this up tomorrow and get this out to you. So, see ya.